Hello everyone, and welcome to this lecture where we're going to be implementing BFS, or breadth first search. So this algorithm provides us with the ability to return the same results as DFS, but with the added guarantee to return the shortest path first. So remember, this has to do more with that word ladder puzzle. So this algorithm is a little more tricky to implement in a recursive manner instead of using a queue data structure. So what we're going to be documenting just the iterative approach, which is most likely what they're going to be expecting in an interview setting. So we're going to be coding out this. All right, so we'll assume our graph is in the form of this dictionary. We have your vertex and then the set of vertices it's connected to. So let's go ahead and implement this out. So what do we do with a BFS? Well, our function is going to take in that graph and that starting vertex. We'll have an object visited, and that's going to be equal to an empty set. And then we'll have a queue, and we'll treat this as just a list start. And you can actually use a queue from the collections module if you want to. We're just going to be popping it off with a specified index 0 to treat it as a queue. So basically what I'm going to say is vertex is equal to queue.pop at 0. So you could just, if you wanted to, from the collections module, you could import queue as we've discussed back in the queue section, or build out your own queue. Maybe you're asked at an interview setting. But anyways, so while the queue is still there, pop it off at 0. So that's going to be that first one. Remember that first in line. You can go ahead and review the queue lectures. And if you say if vertex is not in visited, what we're going to do is take visited, add that vertex to it, and then we're going to use a queue to extend. We'll say queue dot extend, and then I'm going to graph that vertex minus the visited, and then just return the visited. So it's extremely similar to DFS, except you notice we're treating it as a queue, so we pop off at the beginning. So what's actually going on here? Well, the main thing you should notice is that the actions performed per each explored vertex are basically the same as the depth first implementation. However, what we're doing is replacing the stack with a queue. And with the queue, what's going to happen is we'll instead explore the breadth of a vertex depth before moving on. And this behavior basically guarantees that that first path located is the shortest path present, based on the number of edges being the cost factor. All right, so if you want to check out more explanation notes, you can always reference the Jupyter Notebook here. So this is what we just coded out, but there's again code that will actually also tell you how to print out the possible paths. So that's also helpful to know, as well as just printing out the shortest path if it's there or not. And again, some really great resources for you to check out. That's all there is to it. Again, it's really quick if you already know how to do DFS. You're essentially just switching a stack for a queue here. That way you guarantee the shortest path is the one you hit upon first. All right. I definitely encourage you to really read about graphs and DFS and BFS on your own independently. Don't just take everything you've learned from this course, but really you should explore more and use the resources provided for you to really build out your understanding. It really help complete your computer science knowledge as far as graph theory. But as far as interview questions, definitely the most important ones to know is how to implement a graph, how to implement both BFS and DFS, and then another common interview question is basically filling out this function, which is to return all the possible paths. Sometimes they ask that, sometimes they don't, and sometimes they don't even ask graph questions at all, so just keep that in mind. But basically the ones that we ask in this course are definitely the ones that you should really know. Okay, well, thanks everyone, and I will see you at the next lecture.